Welcome students of linear algebra. If you've got an exam or test coming up, or you've just seen this in a lecture and you don't know what's going on, it's okay. Hopefully after this video it'll make much more sense. So before you can even understand how to prove a linear transformation, you need to know what a linear transformation is. So essentially a linear transform is a vector function. So you put in the coordinates for a vector, which could be in 6D, 2D or 3D, and then it could be mapped into the same vector space, or it could be mapped into a different one, like a 2D vector could be mapped onto like a 6D plane, which is pretty cool. Like it geometrically transforms from one space to another space. So in this is a bit different to single and multivariable calculus because we don't have each coordinate representing its own mini coordinate. Like you can think of this as a little mini coordinate system. Like, you know, it's if you're not dealing with vector functions, it's essentially this. You get an integer and you're good to go. But yeah, the reason why we call this a transformation is because you get a massive visual geometric transformation of this thing in a space. So it's pretty cool. Now, how do we know something is a linear transformation? Like how do we know with numbers? So when you add two vectors inside a linear transformation, it will equal the same as just putting those vectors into the linear transformation and then adding them afterwards. If you multiply a vector inside a linear transformation with a scalar, the result would be just the same if you performed a linear transformation on a vector and then applied the scalar afterwards. So in maths, that is what I just said. So let's say you have some transformation, it would be some function of some sort. You can think of this as the equivalent of f of x, but just for vector functions. And you put in two vectors, you add them, and then you put them through the transformation, and it'll be the exact same as just putting the vectors individually through the transformation. And the same goes with a scalar. It doesn't matter if you multiply your vector by a scalar first, and then transform it, or transform your vector first, and then apply the scalar. So how do we go about proving this? Oh yeah, why is it these two conditions? Likely because if you're moving something from one coordinate system to the other, the order of operations shouldn't matter because you're in the same realm but on a different planet, if that makes sense here. Like if one of the conditions doesn't hold, it would be like a cat from a cat planet, not landing on another cat planet within the catverse, but instead on a bird planet in a birdverse. It's just not a... Look, let me show you a photo. This is a linear transformation. This is not a linear transformation. So like if any of your conditions don't hold, it's just you're not dealing with a linear transformation. It doesn't make sense. It's not really mapping on to just a different planet with the same verse. I don't know, if this helps, it helps. So let's do a full step-by-step example of proving that something is a linear transformation with questions that I've done myself with my own handwriting. I've made it as neat as possible, okay? So this is our linear transformation. So this is essentially saying that the domains for each of these functions are of the dimension 2 in the vector space, and we've got two coordinates, and what happens when they go through this function, the x coordinate becomes negative and the y coordinate stays as the y coordinate. So that's what happens when a vector goes through this transformation. So the first thing you want to do, always, all the time, in every single linear transformation proof, is let u equal to some vector, let v equal to some vector, such that uv are an element of their domain that is stated. You also want to state the scalar that you'll be using and that it's an element of all real numbers. It's very important. So step 1, as you can see I've highlighted, make sure you state your u and v, or two vectors, could be t and k, it doesn't matter as long as the reader understands that you've got two vectors and that you're going to use in the proof, and that is what they're going to look like. You also want to state, yes, I said that. Oh, and after that, you want to state the vector you'll get when you add your two vectors together, as well as the vector you get when multiplied with a scalar. This will become evident why later on it's so important to state all of the notations and symbols you're going to use in your proof. But trust me, it's a very good habit to have. Yes, so you don't want to, I included an example. So imagine if every text in the world was written like this. So Joseph, noun person, swung the action of accelerating your upper limb from behind you to in front of you. The vinegar, a revolting acid some people actually eat chips with towards it. Like, can you imagine if every book, like every single word was explained? That would just, it's just far more reasonable to tell everyone the general rules so they can make up their own languages and freely speak between them. It would just waste so much time. And this is why you should always define your symbols and notation beforehand, because it's the English equivalent of doing this, and it's so annoying. So just define your symbols and notation beforehand. Alright, so you've done step 1, which is defining all of your notations. The next step is to prove the first condition. So remember we already defined u plus v, so we can just get straight into it. See how much neater that is? You just get into it. So yeah, you plug the transformation of u plus v, you plug the vector of u plus v into the transformation, and then you evaluate it, and you get this. So these would be the new x coordinates, and these would be the new y coordinates. And so these are what you want to plug into your linear transformation here. So now you want to, after you've done that, you want to prove the right-hand side. So you apply the transformation to each vector separately, and then add them afterwards. So as you can see that, you've applied the transformation here, and after the transformation has happened, then you can add them. And look at that, they're the exact same. Do you know what that means? Since the left-hand side is equal to the right-hand side, the first condition is true for f1. So we're halfway, I suppose, of proving that this is in fact a linear transformation. And goodness sake, never forget to conclude, ever, ever, ever. Always conclude. It's a good, and yeah, that's happy. Yes, I know it says drove, but it's, you know what I mean. Okay, step 3. Now you want to prove the second condition. So I like to denote the left and right hand side of the equation shown, because that's what I use in my proof. So feel free to do that as well. It helps the viewer who's marking, it helps the teacher who's marking your work, and you as well when you're doing the proof. So evaluate what happens when any vector in the domain is multiplied by any scalar which exists in real numbers. Remember, we already defined CU, so it's a nice and smooth proof. You see what I mean? Look how nice and smooth that is. We just define everything at the beginning. So yep, left-hand side there. As you can see, it's all good. And then after you've simplified the left-hand side as much as possible, move on to evaluating the right-hand side. And look at that. It's the exact same. Do you know what that means? The second condition is also true for f1, and geez, never forget, guys, don't forget to conclude. And then step 4 is, because both of the conditions for a linear transformation have been proven for f1, f1 is a linear transformation. And I'm going to rant now. Concluding lets the reader know you're self-aware of what you just did and didn't get lost in the calculations. People who don't conclude get lost in the question and don't understand what the point of the proof is, and this shows lack of understanding, so always conclude. So this is what your working out should look like, which is really important to have structure and notation, so make sure you practice and get the hang of all of the steps, but I'm sure you guys have gotten that. So what happens if something is not a linear transformation? What's it going to look like? What do we do? That's a great question. So you just need to show one of the conditions is not true, either through like obvious examples, or just plugging in some numbers and showing that, okay, since I put this number in here and then I put this number on the right hand side, the left hand side does not equal the right hand side, therefore, the first condition or the second condition doesn't hold, so it's not a linear transformation. So my advice is to carry through proving both conditions, and then through intuition you plug in some numbers, which is what I just said. So let me give you an example. This is something I did. So I came across this linear transform that looked like this, and you can't really tell with most linear transformations if they are a linear transformation. So this is where you want to follow through the steps. So yeah, it's not obvious. So this is what I ended up doing, and yeah, I thought it was 3 coordinates for some reason. I guess I was just really excited. I do get excited about these things, not ashamed to say that. Anyway, as I was working through it, I was doing the first condition, and I noticed that this is what happened to didn't define my right and left hand side. That's very naughty. But essentially, I've just shown that x squared, like the first coordinate squared plus the second coordinate squared, does not equal to that square, because everybody knows that that's those two aren't equal. I really hope you know those two aren't equal. And yeah, that's essentially what you do, or what to do if you encounter something which isn't a linear transformation. You just continue with the proof. If you come across something that doesn't hold, you just stop and you say why you stopped, and that's it. Your question is finished. So in summary, a linear transformation is just a vector function, and a linear transformation must hold two conditions. The first being is that it does not matter if you add the vectors then transform them, or transform the vectors separately and then add them. It also doesn't matter if you multiply the vector by scalar first and then transform the vector in them. Geez, I was getting tired when I wrote that, but you guys know what I mean. You can rewrite the summary for me in the comments, and and can help everyone out and me with my English. So, important advice: 1. Always conclude. 2. Define all notation and variables at the beginning. 3. Always conclude. And 4. Prove the right hand side is equal to the left hand side. And yeah, I'm pretty sure you guys will all be set with proving your linear transformations. Good luck for your exams, your tests, your studying, your lectures, and I hope to see you guys again soon. Thanks for watching.